So we are smart contract auditors, mainly auditing contracts built in Solidity for Ethereum. We also do onboard new people to the ecosystem, for example, through lectures at the Czech Technical University in Prague. And most importantly, we also love building open source. So we've got a tool for Solidity development called Wake. We'll be actually using this one for fuzzing today, and you will learn more about the tool later on as we continue with fuzzing. We also have the pleasure to work with many exciting projects like SAFE, Lido, Axelar, and so on. We've also received a couple of grants, especially for our tooling. So let's start with the main topic, which is fuzzing. And if you want to follow along, you can scan the QR code. You can also check the link, or you can maybe return to it later on. And this one will be also present on each slide, so you can also scan it later on. All right. So first of all, what's fuzzing in general? It's a special testing technique where we generate random sequences of transactions. We also generate random inputs for such transactions. And then we pass all those transactions, we execute them, pass the data to the contracts, and observe how the contract behaves. And hopefully we may encounter some interesting issues, maybe not. So this is fuzzing in general. But today we will be speaking about manually guided fuzzing, which is still fuzzing, but made a bit differently, let's say. So first of all, we obviously need to deploy the contracts. So we need to say how we will be deploying contracts, and we may actually use random data already while deploying the contract. If it's possible, if it's well needed, we can do so. Then obviously we also need to define invariants or like properties we will be testing, because without assertions, without invariants properties, we will hardly find any issues. But what's different about manually guided fuzzing is that we also define how we want to execute the transactions, how we want to generate the data, how we want to pass the parameters, and so on. So this is quite different, and I will be having there an example. So this is an example of an invariant, and actually this is the syntax from Wake, from the testing framework, and it's in Python. So there's some decorator for invariant, then we define the function, and finally make some assertions. It's quite simple, straightforward. And the second one is something we call flow. So again, it's in Python, it's in Wake, and this is where we define how we want to execute that given transaction. So except for like executing the transaction itself, we also define how we want to generate the random data. And this is what makes it quite a bit different, but this is still a very simple example. However, it already shows how this approach is different from, let's say, black box or gray box fuzzing. So we'll be using Wake today, which is a framework. It's a framework for many things. It's for static analysis, for testing, and so on. But we will only focus on fuzzing today. So it's Python-based, it's open source, it's free, it's for everyone. And I would say it was built or even like born for manually guided fuzzing. The reason is because, well, when we're doing manually guided fuzzing, we want to define how we want to generate the random data. And it's easier in Python because, well, Python is very easy to read, to write. And so, well, it's a good idea to guide the fuzzer in Python. And this is a testing framework in Python. What's different compared to other Python-based testing frameworks for Solidity is that it can automatically generate typing stubs. So we compile the project, we generate something called PyTypes, and because of PyTypes, we actually can interact with the contract and see all the functions in the contract and so on. You will see in the example. And there's also support for forking, so we can fork any existing chain and basically bring contracts from the external chain to our local development environment and interact with such contracts. And so we can basically do integration testing or even integration fuzzing. And then there's also test reproducibility, so we can generate, or basically the fuzzer at the start generates a random seed, and based on that random seed, we can reproduce some issue we've encountered, and we can, well, reproduce it again, and, well, debug the issue. And also there's support for shrinking, so once we have an issue found, we can shrink the number of executions. We can basically select all the transactions that are needed for the issue to be reproduced, and we can skip the transactions that are not actually needed. And what's coming up quite well in a few weeks, I would say. Today we'll be using Wake 4 point something, but there's Wake 5.0 coming in the next weeks, and there's a new edition called Wake RS, which is like a new testing, let's say, backend execution engine, and it's like a drop-in replacement for Anvil. So if you know Anvil, which is a local development node, then this is a replacement, but it's well only for Wake. It's in Rust, and compared to what we'll be doing today, it's up to 60x faster than Anvil. So let's talk about fuzzing. Well, this is an example of a fuzz test in Wake. So what we've got here, a few imports. So we import from Wake the testing, some well helper stuff, then also from fuzzing, and finally there's the import from PyTypes. So PyTypes is a module that is automatically generated by Wake, and well, it contains the same contracts with the same path as our like Solidity files. So let's say there's a directory called source, and there's the contract called myToken, and it follows the same path as in Solidity, but this time it's generated for Python. And then there's a class. So each fuzz test in Wake is a class which needs to inherit from fuzz test, and we can name it whatever. Well, this time it's myToken fuzz test. And there we can define some variables, and those variables will be used for like storing the deployed contracts, but also for keeping the differential state, because we will be doing differential testing. So we'll be keeping our own differential state in Python, how we think the state in blockchain should look like, and later on we will be comparing our Python state to the state in the contract. So this is where we'll be storing all the information. Then there's a pre-sequence, which is like an execution hook. There's a couple of execution hooks, but the only one that's important for today, I think, is called pre-sequence. And it's executed automatically at the very beginning of fuzzing. And this is where we want to deploy our contract. So this is where we assign self.myToken is the contract imported from PyTypes. We just call deploy, and if the contract had any constructor arguments, those could be passed just here. So this is where we deploy all the necessary stuff. Also, we can initialize the contract if it's necessary. What's interesting next, we've got a couple of flows. We've got two flows here, and as you could see at the very beginning, this is where we define how we want to generate random data, how we want to execute transactions, and also what should be a flow? Well, flow should be like a single executable step that's performed by the fuzzer. So the fuzzer sees all the flows defined in the class, and then it randomly picks one of those flows. So there are only two flows, so there's 50-50 chance which one will be chosen. It will be executed by the fuzzer again automatically. And after each flow, there will be all the invariants checked, executed, to make sure that we didn't break any of those invariants. And this is visualized basically in this diagram. So we don't call about, it's called automatically the pre-sequence hook, where we deploy the contract. Then there's one flow chosen randomly, and after the flow, there are all the invariants executed. If they execute successfully, then we can continue with the next flow. This time it's flow X, but it could be Y again. And again, we just execute all the invariants. And this way, we can basically make sure that if there was an invariant broken, then we are quite sure that it was broken in the previous flow, because, well, we are checking all the invariants after each flow. Oh, sorry. So this is about flows, invariants, how we want to define them. And finally, since Wake is built on PyTest, which is a testing framework for Python in general, we need to define like the entry point for the test. It's called test myToken in this case. It's also decorated with something like chain.connect, and this is where we attach to a chain. And well, in our case, this is the code that will be launching an Anvil instance. So it will be launched automatically. We can also specify some extra parameters here. For example, that we want to fork from some RPC URL, or that we want to change the default number of accounts that we will be having. But well, we can basically specify some basic parameters about the chain itself here. And then we just create an instance of our own class, and we can call .run, where we specify two parameters. The second one, 100, is how many flows we will be having in this sequence. So in this example, we have only two flows, but well, this is where we have defined 100. So let's say that we would have 100 flows executed, and then there would be a chain reset. So we would be starting from the very beginning, and then it will there would be another flow, another sequence after the chain reset. We would be calling, or it would be called pre-sequence again. We would be deploying all the contracts again, and again there would be 100 flows ran. Then again chain reset, another sequence, another pre-sequence hook, another 100 flows, and so on. And this then, the first argument, is how many sequences we want to execute until the test finishes and it exits because we've run all of those sequences. So this is like the basic state machine that's automatically integrated into Wake, and well, it's all basically implemented in this fast test class. So we can use this one to define like executable steps as flows, pre-sequence as the function where we deploy all the contracts, and finally invariants to check, to make some assertions about our code and check them automatically after each flow. So I hope it made sense, and I can continue if there are no questions. It looks good, I guess. Okay. So let's talk about some best practices, because well, manually guided fuzzing is especially about defining flows, invariants, and I would like to focus about on like the best practices for defining flows, invariants, and so on. So the best recommendation I can give is to execute only one transaction in each flow. So each flow should be like dedicated to a specific function, to a specific transaction, but there are a few exceptions. And like, I think the most common exception is if our function that we are about to execute, invoke in a flow, is about to accept some tokens. If it needs some tokens, then most likely we need to make approval before the transaction. So this is like the only maybe, or like the most common exception to this recommendation. If we need to also supply some tokens, that it's usually absolutely fine to make the approval and then finally execute the transaction that we are intending to execute. The next recommendation is to also check for events and errors, because well, what I've seen in fuzzing in general, sometimes those things are not checked, but I believe these are also quite important, so this should be checked too. Then what's well maybe quite interesting one is that view functions should be only used for invariants and not for executing transactions. I will have a nice example in the next slide, I believe, but well, it may seem a bit weird, but since we will be keeping a differential Python state in our test, well, we don't need to call the view functions because we should have our own information, our source of information, and we can use it for executing the transactions. And so it doesn't make sense to run the view functions on the contract. Yeah, as I said, we should keep our own Python state and use it for generating of parameters. Also, if it's possible, it's not always possible, but well, if we can, then we shouldn't look into the Solidity code because we want to be unbiased. Well, when we are doing fuzzing, or well, let's say manually guided fuzzing, we shouldn't be the ones who have written the code in Solidity. We should have some basic knowledge about the code, how it should probably behave. We should perhaps have some assumptions about the code, but we shouldn't be the ones who actually wrote the Solidity code. So we shouldn't even look into too many details of the code. Also, again, if it's possible, we should avoid mocking contracts, and instead we should do integration fuzzing, so fork from a node and then use real contracts that will be deployed on the mainnet or whatever chain it is. instead of just creating mock contracts, because mock contracts won't be used in the actual environment once we deploy our contracts to the mainnet. And also one, again, quite weird recommendation, but it's for reproducibility of bugs found. We shouldn't use the default set in Python, which is, well, yeah, present in Python. Instead, we should be using ordered set, which is like external package. The reason for this is that the insertion order of sets in Python is not deterministic, and so we might be encountering like different behavior even if we supply the same random seed. So this is one example of why we shouldn't be using view functions for testing our contracts except for invariants. So let's assume that we have a contract that consumes ERC20 permits, and we also have a permit defined in our token. And this is the definition of the type hash for the permit. Then we have also a function to get the hash of a permit itself, of an instance. There's also a code to get the final typed hash, which includes also the domain separator and the data itself. And then let's assume that we are testing a function on some vault or whatever it is like this. So we take the type data hash of our permit, sign it, pass it to the contract. It's a bit simplified, and well, the first three code snippets are in Solidity, while the last one is like pseudocode, maybe in Python. It's not very important, but well, we are using a view function from our contract. And what's the issue here is that it will most likely succeed. That's the issue. And the issue, it's an issue because there's actually a bug. I don't know if anyone had a chance to find it, but there's an extra space in the type hash, and so the type hash is incorrect. It's not according to a EIP 712 definition. And as I said, it will succeed, the transaction will succeed, and the reason is because we've used a view function. So we've trusted the contract that we are actually testing, and we've passed the information from the contract we are testing to the same or maybe similar contract again. And so we've used the same source of information, but the source is untrusted. So this is an example, maybe not the best one, but it's quite simple, of why we shouldn't use view functions except for assertions. And how it can be done differently? Well, this is an example in Wake, but what's important here is to show that what's powerful is differential testing. So we can define a permit data class. We can use this type of, these basically typings that are also supported by Wake. And then we can do something like that. So we can define our permit. Then we also need to specify IP712 domain. Then we can call something called sign structured, and this function can actually compute the type hash, and it doesn't take it from the contract itself. So that it's a different source of information, and because of that, it will use the correct type hash, and so the transaction will fail. And that's the difference. So if there's a chance to invoke or like do the same thing as in contract, but in a different way, which means in Python, instead of taking the information directly from the contract, we should take the chance and define or like invoke the action quite differently and do differential testing. So that's the whole point that we have Python. And so we can simulate basically the same thing, but in a different way, in a different language, and then compare if what we are assuming that the contract will do will be actually done. So these are the final few slides. I check how many minutes we've got left. All right. So this is an example of a flow, how it should look like. So let's say we have a flow for deposits. So first we define some random parameters, how we want to execute flows. Then if there are any preconditions, which are especially tokens, we need to somehow get the tokens, approve the tokens for the contract we'll be interacting with. Then we execute the transaction. We may also expect some rewards, so we may also wrap it with a may reward block. then we should check for the errors. As I said at the very beginning, in the recommendations, we should be also checking for errors if there are any, also for events. And finally, we should update our local Python state so we can later make invariant or like assertion about this Python state compared to the state in contract. And I think this is all of the slides. So I would like to, yeah, open my VS Code and show you some coding. All right. So I've got an example project here, and this is a very simple template. And as you can see, there's basically nothing. And I didn't even write the contract, so I know just a few information about the contract, which is like, I think the best opportunity how to show you how to interact or like manually guide it fast, even the contract that you don't know. So first of all, I will open my terminal and I will execute something called wake up by types, which will generate the typing stubs. So when I check these imports, I can see that the Python extension actually knows about these files. It can even see something called single token vault, which is a contract that's defined in my project. I can even show you that there's contract, there's vault, and the name of the contract is single token vault. But I have it generated in Python, so I can even show you. Well, it's not intended for humans to be read, but it's especially for like auto completions by the Python extension and let's say Copilot and others. So I will close it for now, and let's start with writing some code. So we have the class here. We do inherit from fastest, and now it's the best time to deploy the contract itself. As you can see, it expects some parameters, a token. So well, let's assume that we'll be supporting only one token, and in this specific case, there's one token contract already defined. It's a mock. As I said, it's not the best idea to use mocks. So I will start with this mock, and later on I can even show you how to do integration testing with forking. But I will start with this mock ERC20. As you can see, the Python extension knows about all the functions because of the PyTypes, because of the typing support. What I also like to do is to just define that there will be some variable defined in the contract just to track the variables defined, sorry, in the class, the variables defined inside the class. So there will be a token, there will also be a vault of this type. And now we can finally pass the parameters. As you can see, it's underlined because, well, the constructor in Solidity has uh, 3 parameters, and so even the Python typing stub expects 3 parameters. So the first one will be self.token, and then there are 2 more, min deposit, max deposit, and well, let's say that min deposit will be an integer, max deposit will be also an integer, and we can start already with some like randomization of parameters. So let's say that min deposit will be random integer in between 0 and 100, while self max deposit will be random integer in between, I don't know, yeah, for example, this one, that sounds good. Min deposit, max deposit, and I will also format the code. Yeah. So we should have the contracts deployed, and just to make sure it works, let's run the test. So we'll be running wake test slash test, and the name of the file should be test vault fuzz. And I will also append dash d to debug if there's any assertion or any error. So yeah, I can basically attach the debugger. And yeah, it succeeded. And there's also some statistics shown. So as you can see, it executed flow something 100 times with 100% success. There's also the random seed. And yeah, I think this is the most interesting part. And yeah, there are also some logs defined in the fuzz test itself. And if you check the flow, then it does just nothing. So it's quite expected that it passed. But well, we deployed the contracts. I can even insert a breakpoint here. This is quite useful for debugging. So if sorry, I wanted to show this one. If I run the test again, I'm right after the execution or like deployment of the contract. I can even check if the contracts were truly deployed, like with self.vault. So there's some address of the vault. I can even check the code, whatever. I can even check the transactions themselves. So I can use chain.txs. -1 is the latest one. And I can, for example, check the call trace. Yeah. So, or maybe just events. So this is quite very powerful for debugging. Anyway, let's continue with manually guided fuzzing. And now we'll be renaming this flow to flow underscore deposit, because if I remember correctly, there's a function called deposit. Yeah, there's one. So I will skip the beginning and I will try to execute self vault dot deposit, and I need to specify the amount, and perhaps I also want to specify who's the sender of the transaction, like who's calling this function. So let's generate the amount, and let's say it will be a random integer in between 0 and well 1000. And since it's a deposit function, it will most likely expect the tokens we've attached, or like the token we've attached here in the constructor. And we've got two options. If there's a mint function on the contract, then we can execute it, or there's a cheat code called mint ERC20, where we can just set the token. We can set the sender or like the recipient of the tokens, but we don't have it generated. So let's say that the sender is a random account, and we can specify it here, also the amount, and then we can say that the transaction will be sent from the sender. So this time, well, we can basically define all the parameters. All of those parameters are randomized under our control, and I believe we also miss here an approval. So yeah, that looks good. Now there's the transaction sent. I will insert a breakpoint here, and then I will update the Python state because we want to track the deposits from different users. So let's make a dictionary, deposits, which will track the deposits from different accounts. And I will use something called default dictionary. And it's kind of like mapping, where we can define the default value if it was not accessed before, and we want it to be 0 as the same way as in mapping. But what's different here is that we can iterate over the default dictionary, so we can see all the keys that were set or like accessed. So let's say that self deposits will be a default dictionary. And if I just pass here an integer like int, it will default to the 0. And so in the deposit flow, I can track the progress, what I expect that happened in the transaction, and it is that the self, the deposits for the sender should be increased by this amount. As I said, the default value is 0, so if we add this value and it was not like accessed before, then it will just assign this amount. And yeah, let's also define the invariant. I will call it invariant deposits, and we can iterate over all the accounts in chain.accounts. The reason is because the random account here takes a random account from chain.accounts. So we have a limited set of accounts we are interacting with. And so it's enough for us to check all these accounts defined or like set it in chain.accounts. So let's iterate over all of them and make the assertion that self.deposits, which means our local Python state, is the same as the state in the contract. So self vault dot, and I don't remember what's the name of the function. Maybe I would expect it to be balance of. Let's try and let's see if it's the correct one. We can remove these lines of code, and I kept a breakpoint here because I want to also check the, the events. So let's run it. Yeah, and we've encountered the breakpoint. I can print tx.callTrace, and I can see there was a deposited event, also an event from the token, but we are not testing the token, we are testing the vault. So we want to also make assertion about this deposited event, but I will quit the debugger for now, and I will remove it just to leave it running for a longer time. And as you can see, we've also encountered and like a reward above max deposit. And the reason is when I check self.max deposit, it's 395, but what we have as the amount is more. So yeah, that's good because we are also testing the edge cases, but we need to handle them in the test. So I will wrap this tx with my reward as ex, and then let's check that if ex.value, or maybe let's use this instance. So if it's an instance of single token vault dot, and I think it was called above max deposit, then let's make an assertion that ex value is an instance, and yeah, it doesn't accept any parameters, so the error itself also doesn't have any parameters, and we want to early return with some custom status like this one. I would also expect there to be another exception, so let's try below. Yeah, there it is, and I think it will be quite similar. And otherwise, let's try, but let's say that there are no more exceptions. So otherwise, let's say that the execution should succeed. And run it again. And it says that it cannot found any flow to run, which is interesting. Let's check. Yeah, I think the reason is because, well, we have this max deposit so low that it couldn't even find like a proper value to 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 execute the transaction. Yeah, and I can also see that there were some successful transactions, and then there was one failing transaction. But since I'm afraid we are quite running out of time, I would probably terminate it here. And I know it was like very fast and it was a lot of information, but basically what was the main idea here is that we deploy the contracts, we define how to want let's say, pass parameters to those contracts, even to constructors. And then we define for each like state changing function in the contract, we define a flow. We define how to want to generate random parameters for the upcoming transaction. We make it succeed if there are any preconditions, and then we execute the transaction itself. We may expect some exceptions. If there are any exceptions, then we make assertions that those exceptions should happen in some cases with some preconditions, and then we finally update the Python state so we can make sure that our local Python state is the same as the state in the contract by invoking this invariance. And we also may like to specify the parameters for how many flows we want to execute and how many sequences we want to run to make sure we've performed a lot of transactions and we haven't missed any issues. Yeah, I can even show you very quickly how we would make an assertion about the events. So it would be like assert, and I believe the name of the event was deposited. So deposited, user was the sender, amount was just the amount, and yeah, let's make an assertion that it was present in tx.events, and I can see that it doesn't like because there's account, but it expects an address, so I will take just sender.address. And this way we can also make assertions about the events. And yeah, so I think that's all for this workshop. It was very quick, but if there are any questions, then yeah, I'm ready to answer them. Yeah. I think you are right because well, we are not checking like yeah. I think it should be actually like that amount is bigger than yeah. Sorry, my mistake. Any other questions? All right, it seems like not. So there's quite a lot of more examples in this project, so you can check them out. There's also signing of EIP 712 data. There are also some examples for unit tests. But well, I especially wanted to show you the manually guided fuzzing with the definition of random parameters and with those assertions. And yeah, it was very simple example, but well, it can be applied to anyhow complex projects. Obviously, the test will also grow by the complexity of the project. But well, since it's in Python, it's still quite well reasonably possible to write that complex fast tests. Okay, so